In this section, we're going to discuss traversal behavior and predictability. This is a really fun and interesting topic that can help you take your graph skills to the next level. So okay, that was cool to say, but what's this guy talking about? For starters, it's important to appreciate that each graph is different. Graphs are kind of like people in that regard. They share certain similarities, but they also have things that make them very unique. Techniques that would work great with one graph might fail miserably with another, and vice versa. It also stands to reason that you're using DSE graph because you anticipate having a large data set. In this case, being able to gather and understand the characteristics of your graph is critical to developing traversals that will perform well at scale. For example, a between centrality algorithm that runs great on a 20-person social network might not hold up so great when scaled to a network with millions of people. And wouldn't it be nice if you can anticipate that ahead of time? Well, that's what we're going to discuss in this section, so let's get started. The factors that affect traversal performance can be broken down into two high-level categories: graph complexity and traversal complexity. We're going to start by taking a look at graph complexity. We'll be primarily focused on characteristics related to the size of the graph and how the vertices are connected. Sometimes we refer to this as a graph's vitals because it's similar to a doctor measuring a patient's weight, height, blood pressure, age, etc. You know, all the basics. No surprises on this next slide. Just like a nurse measuring a patient's weight and height, we're going to start by looking at the size characteristics of the graph. The traversals you see here are pretty straightforward. I'm particularly fond of the second pair where we look at the vertex and edge counts by label, since most of your traversals will likely be confined by label. Quick pro tip: the DataStax Studio bar chart and the Gremlin group count step go together like peanut butter and jelly. If you work through the exercises, you'll get to see this in action. But either way, I highly recommend giving it a shot. Once you know the general size characteristics of your graph, you can start to look at how the data is connected, which is when things really get interesting. And just to motivate this a little bit, the reason this is so important is because these are the characteristics that will influence how much data a particular traversal touches as it executes. These three Gremlin traversals that you see here basically all do the same thing, which is that they compute the degree distribution of the graph. The first traversal looks at both incoming and outgoing degree, and the later two are specific to in degree and out degree respectively. The output of these traversals is also really easy to visualize using DataStax Studio. Highly recommend you give it a shot. It can be very enlightening to see this information in a visual format. It's a really great way to get familiar with the aggregate personality of your graph. In these traversals, we're looking at information that's fairly similar to the previous, but we're getting more of a summarized view, so to speak, by inspecting the mean, minimum, and maximum edge counts per vertex label. I'll point out that when you're thinking about traversal performance, the max order is probably the most critical value because that influences the worst case scenario branch factor. What do I mean by that? Well, suppose you're executing some sort of social network analysis algorithm. It might run great for most folks, but things could go off the rails when you run into someone in the network who is super ultra popular and has millions of adjacencies. So you can get a feel for that risk by looking at these metrics along with the degree distributions from the previous slide. All right, I think it's time for some pictures to help clarify what we're talking about here. As I mentioned earlier, graphs are kind of like people in that they share certain similarities but also have characteristics that make them very diverse. And you can really see that with these three graph types. The lattice graph is extremely uniform. Each vertex has exactly 2, 3, or 4 edges. This is a very straightforward and predictable graph. Then we have the scale-free graph, which is designed to mimic the power law degree distribution of most naturally occurring graphs. This is probably the most interesting graph type because it tends to show up very often in nature, real-world scenarios such as social networks, protein-to-protein interaction networks, semantic networks, and even airline networks. Then you also have your random graphs. And honestly, I think the most interesting thing about them is that early graph scientists thought that they would be great for simulations, but in fact found later that they're typically not very accurate. Like I just mentioned, a scale-free graph would probably be a better fit for most graph simulations. That said, it's still important to understand the different types of graphs, what their characteristics are, and how to spot them. So let's look at the degree distributions for each of these types. In these charts, the x-axis represents the degree, and the y-axis represents the percentage of vertices that have that degree. The lattice graph is really simple. Because each vertex can have 2, 3, or 4 edges depending on whether it's a corner vertex, a side vertex, or one on the inside, you can see that the distribution is very uniform. Obviously, there are only 4 corners on a square, So the number of vertices with degree 2 will be fixed at the count 4. The number of edge vertices is determined by width and height of the lattice. All the remaining vertices make up the area on the inside. The random graph will have a degree distribution that roughly follows a Gaussian distribution. And again, I want to point out that you should probably resist the urge to blindly use random graphs for simulations. There are situations where that might make sense, but in most cases, you'll be more accurate using a scale-free graph, which, as you can see here, has a degree distribution that follows a power law curve, which means that most vertices have a small number of edges and a few vertices have a very high number of edges. If you think of the obligatory social network example, you can imagine that most folks fall on the left side of the graph. Humans tend to have a monkey sphere of approximately 100 individuals, so it's pretty common to see friend counts in this range. But then you have your celebrities, your politicians, your super famous people who have extremely high number of friends or followers, and those are the individuals that make up the long tail of the power law curve. All right, so let's work through an example where we collect the vital graph metrics and start to think about how these different graph characteristics will influence our traversal performance. As you just learned, we start by looking at the size of the graph, and you can see here that the cycle graph and star graph have identical sizes of 9 vertices and 9 edges. It should also be immediately obvious, though, that their degree distribution and other degree-related metrics are very different. In the first line here, we take a look at the degree distribution, and we can see that it's pretty simple. Every vertex in the graph has 2 edges, so we see that for degree 2, there are 9 vertices. And you can see that the behavior of these traversals is very predictable. We sample a random vertex and then begin a breadth-first search over all of our adjacencies, and you can see that our counts increase very predictably. Additionally, you can see that the simple path is always the same. So let's contrast that with the star graph. Here we're running a very similar traversal, but note that the results are quite different. If we look at the degree distribution, we can see that there are 8 vertices with 1 edge and 1 vertex with 10 edges. So you can see how different our counts are for a similar breadth-first traversal like we did on the previous slide. And the same goes for the simple path count as well. The key takeaway here is that we started with 2 graphs of equal size, but quickly learned that the traversal behavior of identical traversals was very different because of the characteristics of how the vertices in the graph are connected. And that's really what this is all about. You want to get familiar with the characteristics of your graph so that you can make accurate predictions about how it will behave in different traversal scenarios. So what did we learn? For the cycle graph, we saw that the flat degree distribution led to a very predictable traversal performance. On the flip side, we learned that the star graph has a more skewed degree distribution, which can cause drastic deviations in performance. And trust me, this is really important stuff to understand ahead of time, because it's pretty easy to have a traversal that works great most of the time, but blows up when you land on a supernode like a popular celebrity or a major airline hub. Now let's switch gears a little bit and look at the characteristics of a traversal and how they influence performance. Here are a few things you want to keep an eye on. If you're familiar with the term code smell, then you can think of these as those types of characteristics of traversal smell. These are clues that indicate that you might be doing something a little suboptimal. For starters, if you have a large number of steps, then you're introducing additional computational complexity. Nothing surprising about that. More steps, more work to do. The next 2 items are kind of related. If you're traversing down long paths or iterating over a particular operation many times, then DSE graph is going to need to do a lot of work and/or touch a lot of data. Again, this seems pretty obvious when you think about it, but remembering to consider these things usually turns out to be the hardest part. Be careful about how you use side effect steps. Side effects take up a lot of memory, which can become an issue at scale. Lastly, be aware of how much data a traversal is going to touch. If you're performing a full graph scan, which I would like to point out is a risky operation that should be done with care, then you need to be cognizant of how much data you're going to touch and what the realistic performance of that will be. There are a few Gremlin steps that tend to be more expensive than others. Not all the time, but these are steps that you should be careful with, starting with the most expensive, your path steps. All of these steps require some path history, which is quite expensive from a memory footprint perspective as it gets saved for every traverser. So we talked a lot about how to identify potential hazards, but we haven't discussed yet what you can do to work around them. Now there's no single right solution here, so my best advice is to be smart and get creative, but I can provide some guidance. For starters, sometimes you may have no choice but to modify the graph itself. I've definitely seen folks who were successful by eliminating outlier supernodes from their graph in order to achieve acceptable performance in a way that did not noticeably alter their results. More often than not, though, you will be focusing on improving your traversal. The first step in that effort is always to minimize your initial working set to the greatest extent possible. You want to utilize indexes wherever possible, and in some cases, you can even rethink your approach, get the same or similar results using a different technique. As we discussed on the previous slide, side effects can be very memory intensive, so you want to use them cautiously. Lastly, sometimes it might be possible to get an acceptable result by sampling and/or limiting your working set. If you want to learn more about this topic, then I encourage you to search DataStax Graph Vitals, and you'll see a DataStax blog post titled Grapho-Endodontology. Thanks to my buddy Dr. Marco Rodriguez for choosing a title that's easy to say on camera. Great post though, I highly recommend reading it. Finally, I want to point out again that a lot of these concepts aren't super complex. In practice, the tricky part really tends to be remembering these simple ideas and applying them. It's easy to get caught up in the initial implementation and accuracy of your traversal without considering how it might perform at scale. So the best advice I can give you is to simply take the time to consider these things. You now have the tools, so when the time comes, put them to work and give it a test run in the exercise.